Let's finally come to our last section in this chapter, multicasting. I will again explain some concepts and talk about what is multicast, what are groups, and how does routing work in a multicast scenario, because so far we basically only discussed Unicast. So up to now, unicasting, but maybe it's a good idea to use group communication, multicasting. Remember, Unicast, that was point-to-point communication. Broadcast was one to an arbitrary number, but multicast was one to a group of receivers. So group communication is a good idea, for example, if you broadcast using IP television certain TV programs. So you simply downstream your TV program over the internet, and you have a certain number of receivers. Also for voice and video conferencing, this could be a good idea. Collaborative work and MMORPGs and massive multiplayer online games, role-playing games, distributed self-organized systems. So there are many applications that may benefit from this group communication. Why? Well, the point is Unicast is not really efficient. Think of having a sender, maybe with a TV program or a video or a concert, and you, as a receiver, you want to watch this concert. There will be an individual data stream from the sender to the receiver, Unicast. And if now the second viewer joins, there will be a second data stream also to this receiver. But we already see that the first and the second transmission contain the identical data packets, so you have to replicate the packets. So you generate a high load, which is not really necessary. So you perform multiple transmissions and you have to execute them sequentially. It's really inefficient. So what is a better idea? Well, you could do this the other extreme. You could broadcast. Broadcast is more efficient. You see here, we transmit only one copy and we replicate in the routers to all receivers. That is broadcast, one to all. So, okay, low load on this very first link, but you flood the whole network. So that's also not very efficient. So Unicast is not efficient because you increase the load on these first links, because you duplicate all the packets. Broadcast is not a good idea because you transmit to many receivers and maybe not everyone wants to see this concert, as an example. So what is the solution? The solution is multicast. So multicasting, you transmit only to the receivers that really want to receive something. At the same time, you will not send duplicate packets over the links. You replicate if needed in the routers, but only if needed. So the network replicates the data, more specifically the routers do this. So that's the most efficient way, that you send your data only exactly to the receivers that need the data, and you don't send it twice or 3 times, etc. Imagine a concert with 1 million viewers worldwide. You would have to generate 1 million traffic streams if you do it in a very simple and stupid ways. So what are the challenges? Well, how do I subscribe? How do I indicate certain interest in the group? Because now somehow in the reverse direction upstream, you have to indicate, hey, I'm interested. Otherwise, how should the router know that it has to replicate now the packets? So interest. And then also the question is, how do I create now my forwarding paths for this multicast group? Because now this is different. We just learned BGP and OSPF, etc. We take the network prefix and then we learn where it is. We learn a certain path. That doesn't work here. And this is why we have IP multicasting. Original specification is quite old, 1989 by Steve Deering. And the idea here is that we use a single group address. A single group address to indicate the address of this multicast group. And this enables a multicast sender to deliver data without knowing the individual hosts. So as a sender, we do not know who subscribes to my multicast stream. That's the idea. This is why we have special addresses for this, multicast addresses, already in IP version 4. You see 1989, that's quite old. There was no IP version 6. And these are our class D addresses, the classical class D addresses, 224 dot whatever. They indicate multicast groups. So these are not individual hosts, but multicast addresses. We need some additional protocols to manage the group memberships, like the IGMP, Internet Group Management Protocol for IP version 4, or the Multicast Listener Discovery for IP version 6. And all this multicasting is done parallel to the classical Unicast. And also we have to map multicast addresses to layer 2 addresses, because in the end we have to deliver our multicast stream to a specific host. Okay, so how does it work? Well, first of all, some more properties. Typically, we use UDP more in the next chapter, what this exactly is, as a transport protocol. We don't use TCP and, well, why see layer 4? Typically, we also do not apply any error detection flow control on the lower layers, if required, then on the application layer. The reason also is that in the end, if we have many participants, we may have so many different requirements, also in flow control, etc. So we cannot throttle, for example, the traffic flow if one of the receivers has problems, etc. So typically we also identify the data stream based on a classical address, source address, so identification. Classical IP address, I will come back to this. Also, the classical multicast has no closed groups, no authentication, and uses a publish-subscribe paradigm. What does it mean? If we have a multicast sender and we have a certain topology, now simplified, assuming this is where how the traffic goes. Remember, we have typically classical unicast paths, how to reach different hosts. Then the sender announces, publishes that there is a multicast stream, and the receivers, our hosts here, these are all the receivers here, they subscribe to certain streams independent of the concrete sender. I will explain how this works. So it's a bit different from Unicast. So before we receive something, we typically subscribe to a multicast stream. So multicasting, as we will see, is receiver driven. The classical Unicast is sender driven. So in the classical Unicast, the sender starts sending a packet, and this then starts this forwarding across the network. In multicast, the receiver initiates this receiving something by subscribing, as we will see. There are different types of multicasting. One is called an any source multicast. So you have a certain group, a certain multicast group, and everyone receives what anybody sends to the group. So you get some data from unknown sources because you don't know who the group members are, assuming no encryption, nothing additionally on the application layer. So we have a group of hosts in the internet, and if you're part of the group, you can send your data into the group and everyone else will receive it. That's called any source multicast ASM. And then we have the source-specific multicast. We receive only what a specified source sends. So we have one sender and a group of receiver, and we can explicitly select the multicast source, and we can then also filter out, depending on the source, what we want to receive. But there are some more challenges. Well, we do not only have routers, we have to discuss about the routers and how we perform the routing for multicast, but we also have in the local area network, we have switches. Okay, we are here on layer 3, but if you imagine a network where you have a switch, the switch is connected to a router, and now multicast data comes in, the switch has to know over which port it has to forward this multicast data. Maybe only via these 2 ports, but not via all the other ports. Okay, there's always this naive solution or simple solution. We simply flood on all the ports, but the switch, it's better that switch knows which ports belong to a certain multicast group. Oops, okay. So we have a layer 3 concept, but the layer 2 switches have to know something. So that's intra-LAN. So inside a local area network, the switches have to know who belongs to the multicast group. Otherwise, they have to flood. And between the networks, the routers have to know about the receivers. So they have to establish certain routing states to forward our multicast traffic. So you see, this multicasting implies a bit more, not only, okay, this routing of a single packet, but we have to think of switches as soon as we have several subscribers of a multicast group, layer 3, in the same local area network. So how does it work? The first thing is we have to subscribe to something. How does this subscription work? And this is where we can use the protocols IGMP for IP version 4 or MLD for IP version 6. Those are messages encapsulated into IP packets, and they are used between the hosts. These are the receivers of the multicast stream. So we have a sender of a multicast stream. We typically have many routers connected here, and then you have the end hosts, and maybe there are several hosts connected to the router, maybe a switch in between, maybe here. And if here this host subscribes, then we use MLD or IGMP. Subscription, that means I inform the router about a group interest. So subscription will flow exactly the other direction, the opposite direction from the data stream. So then the router, this first router knows, someone wants to receive this multicast stream that comes from the sender. So, and this subscription can be propagated through these routers towards the source, as we will see later with examples. But the routers also, after they know that someone in the network here subscribed to the multicast group, polls if the groups are still present. Why? Otherwise the router will simply forward multicast traffic into the local area network, but there are no subscribers anymore. Maybe you are not interested in the concept any longer, but first you have subscribed and now you're not interested, but the router, you do not inform the router will continue sending data packets into the local area network, but no one listens to the data packets. That's not a good idea. This is why the routers ask periodically if there is still someone interested. And if the switches support multicasting, then they listen, they snoop, they sniff the IGMP or MLD messages and react upon them. Because the switches know the connection on layer 2 to the end systems, and so they also know what's going on if they're able to do so. But you see here we mix now layers. So the switches now will have to be able to understand layer 3 multicast messages. The alternative is flooding. So you flood as soon as there's one subscriber to a multicast group in your local area network, you have to flood the traffic to all systems. Okay, so these are the protocols. For version 4 we have IGMP and with certain features, and also for IP version 6 we have these protocols, and the single source multicasting, you see here a certain RFC. So how does it work now? This very first step. So now we are in a local area network. So in the local area network we use IGMP. So what you see in the examples, with a multicast router, so a router that understands this multicasting, and we have 3 group members, 1 in the upper local area network, 2 in the upper low, and 1 in the lower local area network. Okay, so the router has to know who is actually receiving some multicast traffic. So the router has to know something about the group associations, and typically the multicast groups are only temporary, so the routers have to acquire this information somehow. And that's exactly where we have these IGMP MLD messages. So a multicast receiver, one of these hosts in local area network, subscribes to a group, and this informs the router about the interest. So if you want to receive something, assume you are not a member, then you send this IGMP message, and this informs the router, this host wants to participate. This does not solve the issue, how do I know that there are multicast streams? That's something different, so there are also different solutions for this. This describes IGMP, this describes only the step that, okay, I want to participate in a certain multicast group, and there could be another channel that tells you, okay, there's the multicast group 224.48. whatever. Yeah, you can make this a bit more comfortable, but this is the basic idea. And then you say, oh yes, I'm interested in this. For example, the start of a rocket to Mars, things like this. So NASA started pretty early also with multicasting. And as I already mentioned, from time to time, the routers will ask in their networks if there's still someone interested in a certain multicast group. If not, the router stops sending the packets into the network. Because here in this example, the router has to duplicate the packet and forward the same packet in both local area network. And now also the routers themselves, they have to start building multicast routing trees. I will explain this in some more detail later. MLD, by the way, works in a similar way. So IGMP, MLD, they work in the local area network, and they're basically protocols that are used for announcing memberships. I want to be a member of a certain multicast group. This is why we use IGMP. Not on a global scale. So this only solves the problem for your last router, the router you use to connect to the internet, if this router should forward multicast traffic into the network or not. For the whole network itself, it's a bit more complicated. Because you cannot simply say, okay, I forward then, if there's somewhere a member somewhere in Germany that listens to a concert, I forward the traffic to the whole network of German Telecom or the whole whatever network. It's a bit more complicated. So what we have to create is a so-called distribution tree from the source, here on the left-hand side, the multicast source, to the multicast receivers. There may be a quite complex topology between source and the many receivers. You see here an example with the thicker lines. This is the tree we want to establish, and the thin lines has also a bit more connectivity. So there are different routing paths. So how do we create this distribution tree from a source to many receivers? So just an example, we have a certain multicast source with a certain address. So for real multicast groups, look up, these are the classical class D addresses and this class-based scheme. This was the starting point for multicasting many years ago. So already included in this class scheme of IP addresses, IP version 4 addresses. Okay, so what can be done to create this distribution tree? We have a certain starting point where I say, okay, we know via Unicast routing how we can reach this multicast source. So yeah, this can be assumed the classical routing. There are some other routing paths, but it can be assumed that we have a multicast connection. So how does it now work for the creation of the distribution tree? One approach is flooding and pruning. What does it mean? Well, the multicast source itself can flood the traffic, well, send it to the next router, and flooding is we flood the multicast packets to all the routers. Only the multicast packets. We're not talking about unicast. So multicast from the source. As shown here, we flood it, and so on. And obviously, we will reach, in the end, the multicast receiver here. But we also reach any other node. Okay, that's not a distribution tree. That's just flooding. So now we have to start pruning. We have to cut certain paths. And how is this done? Well, the point is, and this is the reverse path forwarding, the router forwards a multicast packet only if it was received on the proper route to source. So for example, forwarding packets here, that hasn't been done on the proper route to source. Why? We just said that the proper, from this node shown here, route to the source was this one, the Unicast route. So here, this router, well, will definitely not use this data, this multicast data, because this was not received on a proper route to source. Only here, this lower path is the correct one. And the same is true for this upper router. So this is the correct path, but not any data received here. So we forward the packets only if it was received on the proper route. And it's called reverse path forwarding because the proper route was discovered from the receiver towards the source. And we now say, okay, nope, we will not forward if we receive multicast packets on this non-proper path. But still, we do get packets here. Although this is not a multicast receiver. What else do we do? We signal towards the source, this is done by the routers, if there's no need for these multicast packets. So what does it mean? If this router here says, well, I don't need this, but it received the multicast data, because we started our idea, we started this flooding, then it will signal along this proper path towards the source, we don't need this anymore. Okay? And the same here. Well, if no one needs it, then I will signal towards the source, no one needs this. Here, we cannot stop forwarding to the upper line of routers, because here we see that someone needs the multicast packets. Because in the local area network, there was someone who showed interest using IGMP or MLD, telling the first router, yes, there's some interest, please forward. Then the packets will be forwarded here. So the routers will not only first do this flooding, pruning, following the path that was discovered the other way, that's why it's called reverse path forwarding. You will also signal towards the source until the first intersection where we really need the data, that there's no need along their path. So that's the idea. But what happens if we want to participate? Then the multicast receiver, the new one here, says using IGMP, I'm interested to the first router. And then we need additional signaling telling, oh yes, along this path, Unicast, this path, oh yes, we want to participate. And then this router says, okay, I'm not participating, then I want to participate. And this router here finally says, well, I'm forwarding anyway this, okay, then I duplicate and forward this also to you. That's the idea. But we don't have to send data twice over this very first link, or 1,000,000 times. So that's the very basic idea of how to create this distribution tree. So new receivers, they require some additional signaling, as we will see, between the routers to activate this branching. But then, if we are not interested anymore here, well, basically the router will check, will perform the polling. If no one answers, then the router will say, okay, I don't need this anymore. Then this router will check, is there some other network needing the data? If not, I don't need this anymore. And then this very first router will then also check, but there's still someone along the path. As I said, this approach is very simple, this flooding, pruning. But this is implemented in DVMRP, Distance Vector Multicast Routing Protocol, based on RIP, Routing Information Protocol. Unicast routing is not very scalable. You cannot really use it in large environments. So the question is how to scale, how to create maybe a worldwide multicast group. So the idea remains, so we cannot broadcast, but somehow the traffic has to reach the end systems, subscription-based, but how to do it? The idea there is not to base everything on source and the different destinations, but to introduce something in between, a so-called protocol independent multicast rendezvous point. So, a rendezvous point, a special point in our topology, as we will see, where the requests converge, where we maybe replicate the traffic, as we'll see. So the idea was to create a topology with the source, with the destinations, and this rendezvous point independent then on a specific Unicast protocol. This is why it's called Protocol Independent Multicast. And there are two versions. And one version operates, I just explained, DVMRP with the flooding and the pruning, but only if we operate in a dense mode. So dense mode, that means we have many participants of the multicast in a topology. So a larger percentage of the nodes participate in the multicast, then we operate as just explained. But in a worldwide network, it's very unlikely that you have always this dense mode. This is why there's also a sparse mode. And this is now really used for internet-wide multicast groups where you have some hundreds in the US, some thousands in Japan, some participants here and there. And this is not dense. And there we cannot do flooding. So we cannot flood in the internet and then prune. But we explicitly construct a tree using these rendezvous points. The idea is to introduce an additional element. Okay, so dense mode operates with flooding, pruning, and sparse mode now introduces a new element. So now we focus on these more widely distributed groups. So low percentage of nodes will subscribe. High percentage, that's our dense mode. Then we do flooding and pruning, because then flooding is worth doing because you have many participants. Here, low percentage of nodes. So what do we have? We have many so-called multicast receivers, and they want to join a multicast group. We use IGMP to join the local subnet. I've explained this already. And what is new are now our rendezvous points, RP, and they use a protocol element called PIM join. So to join this tree that we want to create. And the routers forward the join message to this rendezvous point, as I will explain with several examples. So the idea is you have those receivers, many receivers, and within their local area network, we use IGMP to signal the router here, I want to participate. And this is done in all these local networks. And as long as there's at least one receiver here in a local area network, the routers will forward the multicast traffic in these local area networks. Okay? And then we will see we have special rendezvous points here, and the routers in between, their job is to forward join messages to the rendezvous point, as we will see, across many other routers. And somewhere we have the multicast sender, and the rendezvous point then issues also a join message to the sender. If there's at least one participant, via IGMP signaled the router forwards the join messages via several routers to the rendezvous point, if there's at least one receiver. So that's the idea. So you also use these join messages, as we will see, between the rendezvous point and the sender. And the sender then sends also a message to the rendezvous point, register message, to say, okay, I know you want to receive my multicast data. And as we'll see, the rendezvous point starts distributing data along a multicast tree. Okay, so how does it work in some more detail? This was a very rough sketch. The first step is that, well, we have here our receiver uses, not really shown here, our IGMP, a message, I want to participate in a certain multicast group. Again, how we know multicast group, this is out of the focus here of these protocols creating the multicast tree. I want to join this. The router then sends this join towards the rendezvous point, as we see here. And after that, we have established this part of this tree, which we'll later then use to forward our multicast traffic. So now we have the shared tree, and the routers along this tree, they have to store state that there's a receiver of this multicast traffic. What happens next? Well, we have to, if there's interest in this subtree, we have to send the join message towards the source. Here the router knows it, and towards the source to say, okay, we now want to receive our multicast traffic. This then creates, as shown here, the so-called source tree where the traffic follows from the source to the receiver. So the idea is that we've, driven by the receiver, create or start creating this multicast tree. So far we don't have a real tree, we have this path. And we create state only along the source tree. So we have different messages involved in this, that's not the main part. But as you see here, so the idea is now to create our tree in the end, consisting of this first part where the traffic flows from the source to the rendezvous point that flows, well, here along this established path, and then down the shared tree to the receivers. There's some additional registration messages and register stop messages, but in the end the idea is to create this path from the source to the rendezvous points, and then from the rendezvous points, so we have this shortest path here to the rendezvous point, and then from the rendezvous point we let the traffic flow down the shared tree to the receivers. There could be more than one receiver, shown here is only one receiver. Okay, so the traffic flows as shown here, and now there are many ways of, well, optimization, creating shortcuts, etc. And one way of optimizing is to find a shorter path. So maybe this path is shorter from the source to the receiver. This is also integrated in this protocol, so you can create shortcuts. So routers of receivers here, they can join so-called source trees. Source trees, that only means a tree originating at the source, as shown here. And in the contrast to the shortest path tree with the rendezvous point, this shortcut is then a mechanism that allows this multicast traffic to bypass the rendezvous point and be forwarded directly from the source to receivers via this last hop router. So you see, mechanisms like this can improve efficiency of the multicast traffic, reduce the load on the rendezvous point. So the basic idea is to use the rendezvous point, but if there is a shortcut possible, then you also can use the shortcut as shown here, and then we can use prune messages, additional messages, to cut the traffic from the rendezvous point to downstream to the receivers. The traffic then flows down the new branch of the source tree. So the source tree starts here and the source tree goes to the rendezvous point, and now we have a new branch here and the traffic flows this way, and you have certain states that you have to store in the routers along this tree, and we can now actually cut off the traffic here. It's not needed any longer, and so this original source tree we had to the rendezvous point is not needed any longer because the traffic flows like this. So Pruning helps cutting branches of the tree, and in the end the traffic no longer flows via the rendezvous point. So this offloads a bit. And this helps us achieving optimal source trees by pruning these trees. But in sparse mode, just think of, well, we have this rendezvous point. Yes, this is where the source tree goes initially. This is where we send our joins, but we can detect shorter paths and create these shortcuts, which helps quite a lot. So this just really briefly sketchy gives you an insight into the mechanisms used to create multicast trees. So it's always the same. We want to create a tree, and there are different ways of doing so. Very basic mechanism was this flooding and pruning. This can be used if you have a dense, so-called dense mode, so many receivers. But if you have a sparse node, then maybe you introduce these rendezvous points, and then you send your join message to the rendezvous point. The rendezvous point is part of this source tree, and then you get your traffic from there, but you can optimize this, etc. So you see there are different ways handling this, and overall, if you look at the group management, you have these different, well, parts where I say, okay, the group management in your local network, this is handled by IGMP, MLD, where you can actually say, oh, I'm interested in a multicast group. And the same is true on the side of the multicast source. And in between, we have this multicast routing protocols, like we just saw this PIM, one with dense mode that works with this flooding and pruning, and where we have the sparse mode where we use rendezvous points, plus we can optimize to create these source trees. In the end, we always want to create a kind of an optimized tree. So multicasting is there. Multicasting is also used, but also for multicasting, there was a larger hype for multicasting in the 90s than it is today. So it is used, but to be honest, not to the extent it could be used. So for many, for example, live streaming, etc., we still see Unicast connections directly to some content delivery networks and not this multicast. But multicast is in use. So the basic idea, again, between the multicast and the unicast is that unicast is sender driven. What does it mean? If you have a sender, then the sender starts sending a packet with destination address and many other things like source address, etc. But the destination address is then taken in all the routers to forward the packet until it reaches the receiver. So it's sender driven. Multicast is receiver driven. So yes, there is a sender of a multicast group, but you have the receiver. And the receiver knows, okay, I want to participate in a certain multicast group with certain IP address, and then sends IGMP, later join messages, etc. the opposite direction until we reach the source, the sender. So it's receiver driven. And then we start sending the data to the receiver. But if others also do this via routers, then we replicate the data here and also send it to this receiver. But it's always receiver driven. So the receivers have to say, hey, I want to join. That's the idea. So there's also an API for multicasting, add membership, drop membership, etc. So that is the idea here if you want to register as a receiver for a multicast group. So you can play with it a bit. What happened to multicast in real world? I just said a second ago, could be deployed a bit more. So the global deployment of multicast is limited. That's also a reason why I really didn't went into all the details of multicasting. Yes, it is used. So intra-domain multicasting, so multicasting within an ISP, that is deployed, IP television, gaming, etc. But multicast between ISPs, so inter-domain multicast, very limited deployment. So yes, there are efforts to make it more available, but there are many problems. So the routing, global scalable routing, is hard to achieve. So what are economic incentives? So okay, if you do multicasting, then, well, why should you do this? I mean, if you earn money by transferred bytes, why should you multicast? So if you have 1,000 receivers, why should you multicast? Because then you will only get money once for the bytes and then they're somewhere replicated. But if you have 1,000 receivers with 1,000 unicast streams, you get more money. So economic incentives, difficult. And mobile multicast especially, that's really a bit more complex. So inter-domain multicast, very limited deployment. But inside the domain, yes, this can be used. Okay, so now, summary. If we look at our reference model, TCP/IP, we have only one protocol for layer 3, that's IP. It's connectionless, typically best effort. Yes, we have some differentiated services, a bit. We have forwarding hop by hop, this packet-based forwarding. We have routing protocols. We know now different routing protocols. We know a bit about multicast, mainly Unicast. We know how to control errors, IGMP. We have in IP version 4 ARP, mapping IP address to MAC address, and some other helpers. We saw that there are several problems with the old IP version 4, not only the address space, but also security and quality of service, etc. So already in the old IP version 4, we saw the extension with differentiated services. I haven't touched integrated services. There are things like mobility support with mobile IP, but there are also things like network address translation where we can discuss if this is a good idea. But there are many problems, issues, challenges, and this is why there's the successor, IP version 6, that could deal with some of the problems. But now it's almost 30 years later after standardization, and still we're waiting. There's usage of IP version 6, absolutely, but not even close to, I would say, 80-90%. So some countries only a few percent, some other countries at least 40, 50, up to 60%. We saw that IP version 6 solves many issues, neighbor discovery, address configuration. We don't need NAT any longer. We can automatically create valid IP addresses just based on layer 2 addressing, maybe some hashing. The header is simpler, a bit larger, yes, but faster to process. We can support larger packages. We saw differentiated service a bit more. Multicast, yes, so you get an idea of multicast, but we know it's not really working on a global scale so far. There are worldwide multicast groups, but and routing, we saw a bit more about OSPF and BGP handling many different aspects. It's not only the shortest path, it's about scalability, robustness, and how to achieve scalability via hierarchies. And please remember, don't mix all this with forwarding the routing. So we discussed forwarding, what this really is, really looking up within some nanoseconds, where should I push this packet to which output port. So, some final questions. So what was this idea overall, multicast, the last topic? So what can we do instead of multicast, and maybe what are the reasons why we do something else than multicasting, unicasting, etc. And why is it so difficult to establish this global inter-domain multicasting? And if we look at the protocols, what is the role of IGMP? MLD. So what do we do there? And then we saw we have a dense mode with this flooding pruning, and we have a sparse mode. What is the idea there? That even within the sparse mode, we create a shortcut. Why shortcutting? So the slides give you also pointers to literature. So if you're unsure about some of the mechanisms, please do look it up in literature.